Today we're going to talk about one of my favorite subjects in math, and that is called knot theory. The idea of knot theory is to be able to differentiate knots from one another. What is a knot? Let's maybe get a slightly precise definition here. So a knot is you could think of it as a simple closed curve in R3. So how you might actually want to think about this for now is just take a string and break it apart at one part, and then tie it up as much as you want, and then you have to glue the ends back together. So here I have some of the simpler knots that you could draw already here. So on the left I have the trefoil. This is the simplest non-trivial knot that one could draw. More on that later. And here is the figure 8 knot. So you can see that it kind of has an 8 shape in the middle there. That's why it's called that. This is slightly more complicated. This has 4 crossings. This one has 3. And it should be completely not obvious that these two knots are different from each other. For example, I could also draw this picture of a knot right here. And as it turns out, this knot right here is just a different picture of the trefoil knots over here. So this knot and this knot, you could just move them around in space to make them look like each other. Sometimes it's a little bit easier to tell that two knots are the same. So for example, this knot right here is much more obvious that this knot is equal to that knot, because I could just undo this little corkscrew right here. By the way, if it's not clear what's going on here, so there are like breaks in the diagram, and the breaks in the diagram indicate that this strand of the knot is going over this piece of the knot. So like this right here is like going underneath, and this right here, this part of the knot is going over top. Some people get confused on that. Just thought I'd clear it up. Okay. Actually, maybe I shouldn't erase that yet. Anytime that you have a break in the diagram, you call this a crossing, and in your knot diagram, if you go from one crossing to the next crossing, that is called one strand of the diagram. So let me make that smaller. So this would be one strand, this would be the second strand, and this would be the third strand of the trefoil. Okay. The simplest knot that you could draw is the unknot. Is just a circle. Here are 2 other pictures of the unknot. Here's like an actual like figure 8. You could just undo one of these corkscrews right here, and this would give you the same thing. And on the right, I have like a really ugly looking picture of the unknot. If you just look at this, it might not be clear to you that this is a picture of the same thing, but if you were to do some untangling here, then you could convince yourself that this is another picture of the unknot. So knot theory is it's useful for a good number of things. One of the more commonly pointed out applications of it is in DNA. So DNA can itself get knotted up, and so being able to differentiate knots from each other can help to understand the knotting behavior of DNA. That's one application of knot theory in the real world. And so it is useful to be able to differentiate knots from each other. So already you can see that it's kind of hard to be able to say when 2 pictures of a knot, 2 diagrams of a knot represent the same knot. But the harder question is, how do we tell knots apart from each other? And so the idea for this, let me move this down a little bit. So the idea is to, let me draw some knots. So to each knot, I want to assign a number, basically. So say this knot right here is going to get the number 3, and this knot over here is going to get the number 5. There's going to be a specific procedure that will, so I input a knot and I output some number or something. And if I take two different pictures, two different diagrams of the same knot, so if I were to do this procedure for this knot or for this picture of the same knot, then I should get the same number. And if that were true, then if this were also a picture of the same knot, and if this one were to get a 5 and this one were to get a 3, then we would be able to conclude that these would be different knots. So that's the goal. Some background to get up to there. I want to move some stuff down a little bit. So, okay. What I want to talk about for the background is addition mod p. So a and b are going to be integers. Z is the set of integers, so that's going to be 0, plus minus 1, plus minus 2, 3, negative 3, so on and so forth. Those are your integers. So we say that a is congruent to b modulo p, or maybe I should do n. P usually indicates that it's a prime that we're working with, but this could be any number n. And we say that a is congruent to b mod n if b is equal to a plus a some multiple of n. So in other words, you could think of this as the difference between b minus a is a multiple of n. This is for some integer k. Okay. So yeah, this is what it means to be addition mod n. And the classic example that you see with this is with clocks. So how we usually talk about clocks or time, not like military time, but standard like AM PM time, works mod 12. So for example, if it's 7 p.m. now, in 8 hours, what time is it going to be? Oop, that should be an 8. What's going on? So 7 plus 8 is 15. But we don't usually say 15 o'clock unless you like military time. Usually we would say this would be 3 o'clock. This is mod 12. So 15 is equal to 3 plus 12. So these differ by 12. Same thing up here. So 15 is equal to 3 plus 12. So 15 and 3 are congruent mod 12. So then we would say it's 3 p.m. after 8 hours. If you do prefer military time, then that would work mod 24. So if it's 17 o'clock in military time, and then you wait, I don't know, 12 hours, then what time is it going to be? Well, you do 17 plus 12, and that's 29. And then you could subtract 24 to get 5. So then it would be 5 o'clock military time. Sorry, this was mod 24. So mod 24, 5, and 29 are the same. Okay. Yeah. So quick example, maybe you can try this one. Compute 15 plus 12 mod 17. So maybe pause the video real quick, give this a shot, and see if you can figure it out. Okay, I'm just going to do it now. I'll assume that you've paused and had a chance to try it. So 15 plus 12 is equal to 27. And so, I mean, what I mean by compute this thing mod 12 is really find an integer between 0 and 6 that is congruent to 27 mod 7. Okay, so I'm going to just subtract some multiple of 7 so that I get a number between 0 and 6. I'm not saying 0 and 7, by the way, because 0 and 7 are congruent mod 7. So anyway, 27, that's congruent to 27 minus, 3 times 7. So that's 21. So 27 minus 21 is 6 mod 7. So 15 plus 12 is congruent to 6 mod 7. You could have also done this like 15 plus 12. So 15 is congruent mod 7 to 1 because 15 and 1 are 14 apart, which is a multiple of 7. And then 12 mod 7 is congruent to 5. So